I want to talk about the bifurcation ratio and how to go about calculating it. So remember what the bifurcation ratio is. It is defined as the ratio of the number of streams of one order I divided by the number of streams of the next highest order I plus 1. And this gives us a useful way of looking at the distribution of stream types and sizes and lengths and areas and all kinds of things within a watershed. So here we have some data from a watershed. In the first column, I have the stream order, which ranges from 1 to 5. 5 is the biggest stream. And in the second column is the number of streams of that order. And if the bifurcation ratio is simply expressed as the ratio of the number in one order divided by the number in the next higher order, we can do this directly from this chart. So for example, if we use streams of order 1 and 2, the bifurcation ratio will be equal to 60 divided by 13, and that comes up to 4.62. And we can do this also for streams of order 2 and 3. We'd get the ratio of 13 to 9, or 13 divided by 9, which is 1.44. Between stream order 3 and 4, we get 9/4, which is equal to 2.25. And finally, between the last two orders, I get a bifurcation ratio of 4 to 1, or 4.0. And you can see that they vary quite a bit. So one thing we would normally do is take these and average these four values to get the average bifurcation ratio. And if we average these four, we end up with 3.08. So here's one measure of the bifurcation ratio of streams in this watershed. And it's actually the least accurate way of doing it. The more accurate ways of doing it involve fitting a curve through data and then looking at the slope of that line. And that's what I'm going to show you how to do next. So here I have exactly the same data in the table up in the upper left. I've also included the logarithm of the number of streams. And you remember how a logarithm works? It's the logarithm of base 10. So if the logarithm of 60 is 1.78, that's saying that 10 to the 1.78 is equal to 60. It's probably easiest to see this for the last one here because the logarithm of 1 is 0, meaning 10 to the 0. We know that by definition anything to 0 is equal to 1. So I've just taken the logarithm of all these numbers here. And now I'm going to plot the stream order versus the logarithm. So I'll plot the first one here. So for a stream order of 1, the log is 1.78. So there is 1.8. So it's somewhere right over here. And I'm going to continue plotting each of these data points for the 5 stream orders. So here's what they look like. And you can see that they sort of fall along a line. Not exactly, but kind of along a line. And so the next thing I'm going to do is by eye, I'm just going to try to fit a line through these data points. And here's my best estimate of what that line looks like. Again, I didn't fit this rigorously. I just put a line on and tried to move it around until it sort of fit through the data points. And the next thing I want to do then is calculate the slope of this line, the slope m. Now remember, the slope of a line is equal to the rise over the run, the change in y divided by the change in x. And I'm going to choose this cleverly so that my run is equal to 1, and that would be one stream order increment here. So if I go from, let's see, where would be a nice place to do this? I can go from, let's see, 3, I can go from this point here, that sort of fits on the curve, to this point here, right? That would be, this is the run here, and that is 1. And now the rise will be this distance here. And if I calculate that, that's 0.1, 0.2, 0.3, about 0.4. So the slope here will equal the rise over the run, which is, actually it's negative, I should have said this is negative 0.4, but I'm only going to take the positive part of this. When I calculate the slope, I'll put this in lines to show that this is the absolute value, right? So I want the absolute value of the slope. So it's 0.4 over 1, and that's 0.4. So that's the slope of my line on a log plot. And now the bifurcation ratio will be defined as the exponent of that slope. So it's 10 to the value of that slope. And if I plug that into my calculator, I get 2.5. Quite a very different answer than what I got before, right? But this is a much better estimate of the bifurcation ratio because I'm using a line here. Okay, now let me just show you another way to do this even more quickly that doesn't involve calculating these logs, and that is to use semi-log graph paper. So let me show you how that works. So here are exactly the same data I had before, but I'm not going to actually use this column now at all, because what I'm going to do is I'm going to change my axes. My y-axis now has this funny shape here, and that is a logarithmic axis. It's still plotting the logarithm of n, but I don't have to actually calculate the log to plot the position. I can plot the position directly. So let me sort of show you what I mean here. So I'm going to plot these exact same data on this graph. So I have stream order of 1, I have n of 60. So how does 60 work? Well, there's 1. So in my logarithmic axis, if this is 10, then the next increment, next line up here is 20, 30, 40, all the way up to 100. Now down here, if this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 30, 40, 50, 60, etc., etc. So 160 plots at 1, 10, 20, 30, 40, 50, 60, right up here. 213 plots at, actually it's going to be plotting sort of like here. These are not linear between 10 and 20. They're distorted just like the log axis is. 3, and the rest of these will be real easy. 3 at 9, 4 at 4, 1, 2, 3, 4, and 5 at 1. Plot like this. So there are my data, and you know they should look really similar because in fact the position of these on the axis is exactly the same as when we plotted them directly. But I'm going to follow exactly the same strategy now. I'm going to fit a line through the data, and I'm going to determine the slope. So the slope equals the rise over the run. Now I'm going to do it a little bit differently here to try to save time. Now I'm going to use one, because this is in log unit on the y-axis, I'm going to use 1 log unit as my increment of the run. I'm sorry, of the rise. So at this point, let's see, 1, 1, 2, 3, 4, 1, 1, 2, 3. So this would be, this is 1 log unit of the rise. And now I just need to figure out the run, which is this distance here. So let's see, that's equal to, that's 1, 2.2 for 2.5. Okay, so the rise is 1 and the run is 2.5, and that is equal to 0.4. And now I'm going to take 10 to the 0.4 power just like I did before, and I'm going to get exactly the same answer I got before, which is 2.5. So this is my bifurcation ratio here, estimated using the semi-log graph. It's exactly the same thing I did before. I get 2.5. Now, I want to finish off by showing how this can be done even more quickly in Excel. So let me go to Excel and show you how this works in Excel. Okay, here are exactly my same data, and now I'm going to use Excel's plotting function to make these plots. So let's do the first one where I plot the stream order versus the logarithm. So I'm going to grab both of those columns, and then I'm going to insert a scatter plot like this. I'm going to get rid of the title. I'm not going to label the axes for now. You know that stream order on the x-axis and the y-axis is the log of the number. But I'm then going to take this. It looks kind of like a line, should look like what it did. I'm going to now click on this and fit a trend line, a linear trend line, and I'm going to tell Excel to display the equation on the chart. Let me make it bigger so it's easier to see. I always have to do this. My eyes aren't very good. So there's the equation, and I'm just going to make it easier to see. Okay. So there is my graph. Okay, and I've also plotted I plotted the equation of the line, which is really useful, right? Because the line is of the form y equals mx plus b, so I can directly see from here what the slope is, right? If the line has the equation y equals mx plus b, then the slope m, which is what I wanted before, was 0. It's actually negative, but remember I'm taking the absolute value of it, 0.4068. Just to remember what we did before when we eyeballed it, we got a slope of 0.4. This is even more accurate. So now I can take 10 to that 0.4068 power here, 0.4068 power, and that will be my bifurcation ratio, and I'll put that right up here. So there it is up here. This is my right up there. So there's my equation, 10 to the 0.4068. All right, now, like I said, we can also do this using semi-log and a semi-log axis, and Excel knows how to do that too. So this is even easier. What I'm going to do is grab just the first two columns, not the log. I'm going to once again insert a graph here. There's my graph. Get rid of the title. I don't care about that. And what I'm going to do now is I'm going to highlight my axis, my y-axis, and I am going to, see, I want to format that axis, and this is the key. I want to change that to a logarithmic axis. There you go. So I've changed this to a logarithmic axis, and these data points should look like they're in exactly the same position because they are. And one way to demonstrate is I can just drag this chart directly over the other one, and guess what? The points are in exactly the same position. So the only thing the log axis does is it permits me to plot the logarithm of the number without having to go through the process of actually calculating it. So it's exactly the same thing, and I can follow very, very similar steps now to get the bifurcation ratio. So I'm going to fit a line. I'm going to add a trend line, but now I have to be careful. I'm going to fit an exponential trend line, and once again I'm going to display the equation on the chart. But now the equation is going to be of a different form, and the slope is a little bit more difficult to find. I'll show you how to find it. So here's the same thing we had before. We've got our line, looks exactly the same. We have a different equation now because this is log axis. Now, what I'm looking for now here is the value of the exponent here. So the slope in this case is equal to this exponent 0.9. It's actually negative, right? 0.937 is what I want. So this is the value I'm looking for that describes the slope of this graph. And to get the bifurcation ratio, I'm going to raise the number e to this power, to the 0.937th power. And that will give me the bifurcation ratio. So I'll put it up here in cells F1 and 2. So I'll write in this cell, the way you do the raise to e to a power in Excel is you use the function exp. So I'll type e xp parentheses 0.937. You see that there? And there we go. And we get a very similar looking, right? Very similar looking bifurcation ratio. In fact, they should be exactly the same. The only reason they're not exactly the same is because of the number of significant figures that my equation shows on the graph on the left and the graph on the right. So here is the most precise way to do it. We're using a graph, right, which is better than just taking the ratios 4 times like we did in the very first attempt. And we're also using Excel to rigorously and exactly fit a line through the data, and then having Excel tell us what the slope is and then transforming that slope into the bifurcation ratio.